All right, so the next section the next topic we're gonna address a little bit more is about the normal force, and we've talked about the normal force a little bit. We said that it's anytime you have a surface pushing back. So let's talk a little bit more about that. So what we've talked about is we've said that an object at rest on a table, we know that there's an upward force from the table, right? We have the weight going down, and therefore we have the normal force going back up. And we've said this before, it's called the normal force because it's always directed normal or perpendicular to the surface. So we've talked a little bit about pushing against the wall too, and that's also an example of the normal force. But the normal force, it can kind of vary. What we like to say, it adjusts itself so that the object stays on the surface without penetrating it. So whatever forces are going down, the normal force has to be equal and opposite to the force that it's matching. So this is caused by bonds at the molecular level. The harder you push on the table, they want to keep that equilibrium, so they push back a little harder. And here's just a visual of that. We also know that and see that the net force is equal to zero because it's in equilibrium. Okay, but anytime that we're not on a flat surface, we could be on, for example, a inclined surface. Anytime when we're analyzing forces on an incline, the normal force still has to point perpendicular from the surface. So what we won't do though is we won't change the way that the weight force is. The weight force is still straight down, right? There's always weight going straight down towards the center of the earth. So when we draw this, we're actually going to rotate our x-axis to match the surface. So this becomes our positive x-axis, and this becomes our y-axis. And we do that so it's a little easier to break down the components to talk about them. So the weight force is still going to point straight down. The normal force is going to point perpendicular to the surface, and the angle that we tilt it right here is going to match the angle that our weight force is changing right there. And that is also having to do with complementary angles or something like that from geometry. So a couple common mistakes to avoid: the normal force is not straight up, right? It is perpendicular to the surface, and the weight is not straight in the y direction. It is straight down. So here's a quick check for us real quick. It says a box is sitting on the floor, accelerating upwards. The elevator is accelerating upwards. How does the magnitude of the normal force compare? Well, if it's accelerating up, that means there's a net force up, which means that the normal force has to be larger than the weight, because the weight's the only force down. If there's a net force up, then the normal force has to be larger. And when you're in an elevator, this is when you feel like you're heavier. Now we have a box that's being pulled to the right at a steady speed by a rope that angles upward. So in this case, if I were to draw my free body diagram real quick, I do have a weight force, and we've actually talked about this before with the car being towed. I have this tension force going up and to the right, which means that there is an x component of the tension force, and that helps to take away or helps to balance out the weight. So the normal force itself is actually smaller than the weight. And then, of course, if it's towed at a steady speed, then I do have a force of kinetic friction also going to the left. But in this case, the normal force has to be less than the weight because there's that tension in the x direction that's helping, or sorry, tension in the y direction that's helping pull it up so that it can it experiences less normal force. And I talked about this in class where if I'm pulling something, if I pull up on it, it actually makes it easier to pull because we're decreasing friction by decreasing the normal force. And we'll talk more about friction later. All right, so we got another example problem. A skier slides down a steep 27-degree slope. On a slope this steep, friction is much smaller than other forces at work and can be ignored. So there is no friction. What is the skier's acceleration? All right, so let me sketch this out real quick. That's not a great 27 degrees, but what the heck. All right, 27-degree slope. The person's going down it. So let's think about the forces that are at work. So remember that I am going to tilt my axis so that it goes with the incline. So there is a normal force, obviously, that's going straight up. There is a weight force that's going straight down. I'm sorry, the normal force straight perpendicular to the surface. The weight force is going to go straight down. So let's get a better visual of that. Well, we know that if it's larger, if the friction force is ignored, we know that the skier will accelerate down the hill. And what is causing that acceleration? Well, if I look, there is an unmatched component of the weight. The weight in the x direction is equal to the acceleration of the object. Is equal to the net force, which is equal to mass times the acceleration of the object. So let me clean this up a little bit with a nicer picture. All right, so here's a little bit more of a cleaned up version of this picture. You can see that I have the normal force going straight perpendicular, and I have the weight going straight down. And the net force off to the side here is caused by, as we talked about in the last slide, is caused by the weight in the x direction. So if I'm looking at my picture, or if I'm looking at the math behind it, however you want to call it, there is a normal force, and that's balanced by the weight in the y direction, and then the weight in the x direction is what's causing that acceleration. And probably not the best drawn here, but this is my right angle right here. That's my weight, and we said that this angle right here is equal and opposite to this angle over here. So in here I have my right angle, I have the actual angle right here, and the x component is opposite of the so the x component is opposite. So anytime we use opposite, we're going to of course use sine. So my net force is going to be equal to mass times acceleration, and in this case it's going to be the weight force times the sine of theta. Well, that equals mg sine theta. It's the x component of the weight. So let me go up all the way up top here. So that means I'm saying that ma is mg sine theta. Okay, I have mass on both sides, so I can cancel that out, and I get a equals g sine theta. And if I think back, this would be acceleration in the x direction. If I think back, that is exactly what we talked about in kinematics when we talked about motion on a ramp. This formula is exactly the same as it was before. And that completely makes sense because just because we're analyzing a different way of looking at a problem, it doesn't change the acceleration of the problem. The physics doesn't change because of how we're looking at it. The physics has to stay the same. So I'm going to go ahead and running out of room. So the acceleration in the x direction equals 10 meters per second squared times the sine of 27 degrees, which when I plug that in my calculator, that'll get me right around 4.54 meters per second squared. All right, so we've taken a look at the weight and the normal force. We are going to do a lab real quick next on the Atwood machine, or the modified Atwood machine, which is something that we looked at with when we first looked at Newton's laws and what forces cause. We do have some more practice problems that we're going to do, but now the next thing we're going to do is we're going to jump more into friction and take a look at what the difference between static and kinetic and rolling friction are. And then we're also going to take a look at air friction, or drag, as better stated. And those two we'll take a look at in the next segments.